Let's, any other question? So the next topic is differentials. And now let me go back to Calculus 1, and just by drawing, and this actually, Jake, answer your question. So this is what we learn in Calculus 1. If you have a curve on the xy plane, like so, so actually I want to make it more curvy, like so. So this is y equal f of x. Let's pick up a point right here. Say this is x equal a, and this is f of a. Right, so now I'm going to move it, and I'm going to evaluate something right here, and this is a plus delta x. So what does it mean? It means that this interval is delta x. Okay? And now we draw a tangent at this point right there, and this tangent is the equation y equals f of a plus f prime evaluated at a times x minus a, right? So where is delta x and where is delta y and where is dy? Well, the difference between this point has value of x, that is a plus delta x, and value of y, that is f of a plus delta x, right? And the difference between the two is delta y. So what about dy? Where is dy? Well, instead of evaluating y or f of a plus delta x, we evaluate the tangent. So this vertical interval is dy. And you can see that if we make delta x smaller, then these 2 points, the point on the curve and the point on the tangent, we come close to each other. Okay. So how this translate to 2 variables, or later on multiple variables? We're going to say that if z equals f of xy, then we have the following. dz is this dz is delta f del x at xy dx plus del f del y at xy dy. Or we can write it, because f and z are interchangeable, we can say that dz equals del f del x at, I'm sorry, that's not what I meant to say. dz will be del z del x times dx plus del z del y times dy. That's a much more compact form. So, and this is just dz. It's not really delta z, but it's close. Now we can rewrite the linearization. Okay? So rewrite the linearization. And let me bring the linearization back and show you why we can rewrite it. Okay? This is the linearization, the general form. Okay? I think I missed here something. Yeah. Wow, I missed something here. this is f of AB plus. Okay? So, going back to how this affects our writing here, well, this part is simply dz. So now we can say that L of xy, you see what I'm getting at? And so we're going to say that f of xy is L of xy, which in turn will be f of AB plus dz. Much more compact form, and all because turn out that we have a complete differential dz, which is made of the derivative, the partial derivative of z with respect to x times the differential dx plus the partial derivative of z with respect to y times the differential dy. I'm not going to try to draw it. I mean, there is a drawing parallel to this in 3D, but I think let's see, how much time do I have? 10 minutes. It's tough to draw. Let me see if I can do it better than I did it in the morning. So I'll pick up a generic point right here, and this will be my ABC point. And this point is sitting on a plane, and so I'll make it as at the edge of the plane, like so. I'm sorry, did I say plane? I meant curve, surface. God, I had to go from plane to curve to surface. So there it is, and this is this particular point. I'll project it on the xy, so this will be AB and 0, like so. And now I'll go ahead and give it a little bit of add-on. So if this will be delta x, and I'll make delta x so small, this is exaggerated, so it will be delta x I can consider to be dx, and in this direction I'll give it delta y, and I'll consider it to be dy. Okay, so so at this point, if I'll bring it up like so, I'll be somewhere right here, and actually let me stay with this box. Okay. So this box, on this corner we have A, B, and C. On this corner we'll have A plus dx. At this corner we have A plus dx plus y. I'm sorry, A plus dx, comma y, B plus dy, and C is the same. And at this point right here we'll have all three. Okay, and now let's draw a tangent plane, and let's see if I can come up with a decent drawing of a tangent plane. So let's say this is the tangent plane. It's a tangent plane to the other through that touch the point, tangent at the point. Okay, so actually everything is exceeding toward me. But I want to make a point here. first of all, the difference between the new point after you add delta x and you add delta y, this is the new point. Okay? This is A plus delta x, B plus delta y, and C plus delta z. Okay? So, the difference between the height of this point and the height of the original point will be delta z. Okay? dz will be, you see, this is the projection. dz will be this much. So it's kind of similar to what we have here in 2D, we have here in 3D. And this is not the easiest sketch to draw, but that's the best I can do today. I think it's demonstrative. All right, here's an example. Okay, given z equals x squared plus 3xy minus y squared, okay, we need to find the following. Find dz, b, find, we're going to let x change from 2 to 205, and we let y change from 3 to 296. Okay? We need to find dz and delta z for purpose of comparison. So let's solve this. Okay, the solution, first of all, we can see that for part, let's see. We can go with a equals 2 and b equals 3. Okay, and now we'll do del z del x will be 2x plus 3y. The derivative of y squared is 0, and therefore del z del x at 2, 3 equals 2 times 3 plus 3 times 2, 2 times 2 times 3 times 3. So I believe it to be 13. Del z del y equal, the derivative of x squared is 0, so we'll have 3x plus 2y minus 2y. It's a negative y squared. So del z del y at 2, 3 equals 3 times 2 minus 2 times 3, and lo and behold, it's 0. Okay? So, dz equals 13 times x minus 2 plus 0 times y minus 3. Okay, and dz, as we move from so actually we can calculate, it will be 13 times 0.05 plus 0 times negative 0.04. Okay, I didn't write it, but dx will be 0.05 and dy will be negative 0.04, right, as we make the change. So turns out that this result is 0.13 times 0.05 is 0.65. Okay? If we calculate delta z, it will be f of 205, 296 minus f of 2, 3 turn out to be 0.6449. That's pretty good. Okay. Let me give you one more example here. When we calculate for volume, so in this example, we are given the right or a right circular cone with base radius equals 10 centimeter and height equals 25 centimeter. Okay? The error in measurement, we are given that the measurement error, and I'll put it in absolute value because it can be in either side, it can be either positive or negative. It's within 0.1 centimeter. That's the error in measurement. Okay? For each. What we need to do is find the maximum error when we calculate the volume. So this is, for engineer, this is a very practical issue because no measurement is completely accurate. And you need to know what are the tolerances. So we know that the volume of a cone is, anybody remember? I'm sorry? 1/3 base times height. 1/3 base times height. Okay? And in this case, we're going to say that R equals 10, H equals 25, dr equals dH equals 0.1. Okay? Those are the R sub 0 and H sub 0. And we need del V del R when it will be 2/3 pi R H, and del V del H will be 1/3 pi R squared. And basically we have what we need. We're going to say that delta V, the error, will be approximated by the complete differential dV. So it will be del V del R at 1025 times 0.1 plus del V del H at 1025 times 0.1. So we have the derivative, the value of the derivative at 1025. Then we have 10 times 25, 250 times 4 times 2, 500. So we have 500 pi divided by 3 plus, here we have 100 pi over 3. Everything is multiplied by 0.1. So we have 600 pi divided by 3, or 200 pi times 0.1, it's 20 pi cubic centimeter. Okay? That's the error in measurement. And last, what happens if you have a function W that has x, y, and z? So now we are looking at the 4-dimension. Okay? Then dw, the differential, you can guess, it will be del f del x dx plus del f del y dy plus del f del z dz. Thank you very much, and I'll see you on Wednesday. Raquel, what time did you come to class?